Hi everybody. So last class we talked about coherent and incoherent waves, and we also talk about combination of two waves, and we talk about two very important concept, what we call as constructive interference or constructive and destructive interference. So talking about this, and then we discussed two very important aspects, that is defining constructive and destructive on a basis of a path difference and a phase difference. So let's do a small recapitulations. So I have here, let's say for constructive and here for destructive. So for path difference, let's say for path difference, so constructive, if it is of n lambda, if a path difference is n lambda, and where n is equal to 0, plus minus 1, plus minus 2, plus minus 3, go on, and this is what we call as constructive interference, and where intensity is going to be 4I naught, and this is what we define as either crust combined with crust or torque combined with torque. So the resultant amplitude is going to be double, and then intensity is going to be 4 times. Whereas in case of destructive interference, path difference is going to be n plus 1 by 2 lambda, and where n is equal to 0, plus minus 1, plus minus 2, plus minus 3 goes on, and resultant intensity is going to be 0. This is going to be a dark, this is going to be a bright, we call it as a bright, we call it as a dark. Why? Because there is no intensity. In this case, the crust is going to combine with torque, which gives you 0 amplitude, and 0 amplitude gives you 0 intensity. This is for path difference, and for phase difference we talked about last class. Your phase difference is equal to 2n pi, where n is equal to 0, plus minus 1, plus minus 2. That means the phase difference between let's say this is a phi, phase difference between the two waves is even multiple of 2 pi or even multiple of pi, then again which corresponding to a path difference of n lambda. Again this gives you a bright, and intensity is going to be a 4 times. Whereas in case of destructive interference, if a phase difference is odd multiples, odd multiple means either n is equal to 1, n is equal to 3, n is equal to 5. That means all the time this phase difference corresponding to the path difference of, let's say, a fractional, right? That could be a half, could be a 2 by 3, a 3 by 2, could be a 5 by 3, 2, goes on like that. So therefore this tells you that in this case path difference is always lambda, and this case a path difference is always half lambda or 3 by 2 lambda. In a say it is of a half lambda. So therefore this crust combined with a torque which gives you 0 amplitude. This is all about constructive interference, and this is all about destructive interference. Now having this concept, we are going to study one very important phenomenon called interference. And I talked about last time about the experiment performed by Thomas Young regarding a double slit experiments. Alright, so look at here. So last class we defined what we call as coherent waves. So we say that interference is possible only when if two waves are coherent or if two sources are coherent. Alright. So what is coherent? We defined last class that the phase should be constant, the amplitude should be same, and the wavelength should be a single wavelength. So look at here now. What I'm going to do is I have a, let's say, two slit. Let's say I have a two source. Let's say this is a sodium lamp. Let's say I have a sodium lamp. Sodium lamp is normally a yellow color, and I have a two independent sodium lamp. And eliminating these two holes, let's say this is S1, this is S2. This is S1, this is S2, and this is hole number 1, this is hole number 2. And now let's say that we would expect, there is a screens, we would expect interference on the screens. Why? Because we say that this is a sodium lamp, this is a sodium lamp, both having a same wavelengths, having a same amplitudes. Why? Because the distance are same. And now this is the point. However, what we found is we won't be getting interference. No interference is found. No interference is found. No interference is found on the screens. Alright. No interference is found on the screens. Alright. So now the question arises, why interference doesn't take place on the screens, even though we have a single wavelength or a single frequency light. Now the point is, what about phase difference? What about phase? What about phase difference? So it is fact that when we use a two independent source, these are the two independent source, we say that two independent source never be coherent source. Two independent source never become coherent source. So this tells that two independent sources never become coherent source because the phase difference doesn't remain constant. There is no fixed phase difference. Alright, reason is that no fixed phase difference. So last class when we define a coherent, this is the phase is very important. If a phase doesn't fix, if a phase difference doesn't remain constant, then we say that the two wave doesn't become never become coherent. So when I use a two independent source, the phase never remain fixed, phase difference never remain fixed. And now the question is, why phase difference never become a fix, even though these two are a same frequency or single wavelength lights. This is the reason. The reason is maybe beyond our scope. This is that whenever light comes from an source, there is an abrupt change in a phase. There is an abrupt change in a phase, and in an order of a time 10 to the power minus. This is very, very small. That change is extremely, very, very difficult to absorb. Why? The change occurs within the time of 10 to the power minus 10 seconds. So this is beyond our observations. Alright, however change is taking place. So because of an abrupt change of a phase, alright, occurring within the source while emitting light, that is why phase doesn't remain fixed. So therefore, no interference is found when we use two independent source. Now the question is, how are we going to get interference? Now the question is, how are we going to get interference fringe? How are we going to get interference? Now, this problem was solved by, alright, English physicist Thomas Young, alright, and what he did, he used a very indigenous technique to lock the phase. To lock the phase. So that means to fix the phase. How to fix the phase? How to fix the phase? The problem is how to fix the phase, how to lock the phase. And what he did is, he used a single source. Alright? He used a single source, and if this single source is allowed to pass through a slit, a thin slit, and when this single source is illuminating this small pinhole, and what we get is you are going to get a light like this. And now I am going to use two slit. Now I am going to use two slit. I take a two slit. Now when I take a two slit, let's say this is S1 and this is S2. Look at here now. Now these two slits, the light coming from a same source is illuminating two sources, and S1 and S2 act as a source. These two act as a source. Maybe could be a secondary source, but these two act as a source, right? So this is how he could fix the phase. This is how he could lock the phase, right? So now whatever phase change occurs here, all right, same phase, same changes taking place here. Why? Because this comes from a same source. So therefore, there won't be any change of a phase taking place between these two sources, that is S1 and S2. Again, I am saying you how he locked the phase is that he used a single source, all right, and the single source light is meant to pass through a thin slit, and that thin slit, right, that light illuminating on two sources. And light coming from two sources are now perfectly coherent in nature. Perfectly coherent in nature. Alright, perfectly coherent in nature. Therefore, now you allow a screens. If you allow a light to fall on a screen, now since these two, right, S1 and S2 are now coherent source. Now these two are coherent waves or coherent source. These two are what we call as a coherent source, and the light from S1 and S2s interferes on the screens, and we get interference fringe. So this is how he used, and this is what we call as Young double slit experiment. And then this experiment was performed in year 1801, and these experiments help us to know that light has wave nature. Alright, so now what I am going to do is, now since we have locked the phase, alright, now we would like to start double slit experiment, that is Young double slit experiment. So this is what we have. Now this is experimental arrangement of Young double slits. So this is the source, this is an primary source, and light from a source, light, I have a light here, and this light passes through these slits, and the light coming from these slits falls on the two slits, that is S1 and S2, acting as a source, and light from S1 and S2s interferes or combine on the screens, and it gets interference. And so this is what we have, and these are the interfering fringe. These are the interfering fringe. Alright, and this is how the light travels along a z-axis. The screen is lying on xy plane. This is a screen lying on an xy plane, Alright, so interference pattern occurs on a XY plane. Alright, so this is what we have. And the distance between the two sources is what we call as D. D is a distance between S1 and S2. S1 and S2, distance is going to be a D. And the distance between the source and the screen is going to be, distance between the source and screen is going to be, distance between sources and screens is going to be capital D. Alright, so this is what we have. So now what we are going to do is, we are going to find out the positions. What we are going to find is, we are going to find out position of bright fringe and position of dark fringe. So this is what we are going to do, or angular positions and the position of a bright and a dark fringe. So at what positions we normally get a bright, at what position we normally get a dark, and the bright is what we call as a constructive interference. This is what we call as constructive interference, and dark is what we call as a destructives. And let's say, again I'm putting you, the bright in the path difference is n lambda, and the dark path difference would be n plus half lambda. These are the conditions. Alright, so now what we would like to do is, we would like to find out the path difference, and then accordingly we would like to find out the positions of a bright, first bright, second bright, third bright, and then we would like to find out first dark, second dark, third dark. This is all what we are going to do. Alright. Okay, now so the most important in the point here we would like to do is to find out the path difference. Alright. So let's say first at the center O, I'll say at center O, what is the path difference? S1 S2O minus S1O is going to be 0. Path difference is 0, so therefore we get a bright. Path difference is 0, therefore we get a bright central bright fringe. We call it as a central bright. Now why? Because if a path difference is zeros, then two lights combines. Either the crusts are combined or trunks are combined. So therefore we get central bright. So this is going to be our first. We get a central bright. So central bright position is at path difference is 0, right? Now we would like to say, what about others other than central brights? So let's say a path difference. We would like to say path difference. So we would like to find out path difference at, let's say position point P, right? I say P is a position of n bright fringe. And what is the path difference? So path difference is going to be S2P minus S1P. This is the path difference. S2P minus S1P. This is the path difference. Alright. And this distance is D. Alright, so we would like to find out this path difference. This is what we call as a path difference. Path difference at P. So how to find out this? Alright, how to find out this? So what I'm going to do is I'm going to use a very simple concept. So first I will find out what is 2sp square. What is 2sp square? 2sp is the hypotenuse. 2sp is the hypotenuse, and I say this is d square. This I'm going to use the Pythagorean students. D square plus x plus a d half. This is s2p square. And similarly, what about s1p square, which is going to be again, this is d square plus x minus d by 2 whole square. This is what we have. And now what I'm going to do is s2p square minus s1p square is equal to, I just take up these two minus these two. Okay, if I minus these two, what we are going to get is these two cancel out, and then this 2 is going to get cancelled out. Let's see, I'll simplify this. X square plus d square by 4 plus xd minus x square plus d square by 4. I'm going to put here minus, minus, minus is plus. This is minus, minus, minus is plus, xd. Alright, so these two cancel out, add out. S2p square minus S1p square is going to be 2xd, where x is a positions. X is a positions of a P from center O. X is a position of a P from center O. So this is what we have. This is the final equation we obtained. Alright, this is the final equation we obtained, and then our focus is to get path difference. Alright, so therefore what I'm going to do is I'm going to use identity, that is S2p minus S1p, S2p plus S1p equal to 2xd. This identity I'm going to use. Now we found a path difference. That is equal to 2xd. I'm going to put here xd divided by s2p plus s1p. And how much is, we say that s2p is almost equal to d. Why? Because this distance is very small. If this distance is very small and this distance is almost equal to d, this is approximation I'm going to take, and s1p is approximately equal to d. Alright, therefore what I'm going to get is, so path difference is equal to 2xd by 2d. Cancel out x d by d. So this is the path difference. We obtained. All right, and I say that this is going to be, path difference is going to be x d by d. Now it says, since n p is n bright, since p is n bright, since P is a position of n bright, therefore path difference must be equal to n lambda, which is equal to xn d divided by d. Why I put xn? This is a position of n bright. Why I put this? This is a position of n bright. So once we found the position of n bright, once we found the path difference, so the xn is going to be n lambda g divided by small g. So this is the positions. This is the position of n bright. This is the position of n bright. And I say that n could be equal to 0, plus minus 1, plus minus 2, plus minus 3, goes on. And now similarly, I can get you a position of n dark. Similarly, I can get you a position of n dark. So the position of n dark is going to be position of n dark is same as is again only why, because here I'm going to put a path difference that is equal to here why how I am going is here I'm going to put a path difference is equal to this is the path difference I'm going to introduce. So therefore this is the position of n dark. This is the position of n dark. And where n is equal to 0, plus minus 1, plus minus 2, plus minus 3, goes on. So these are the position. Somehow now we could find the position of n bright and n darks. Alright. So this is what we have. Position of n dark and n bright. So again I told you that screen is on an xy plane. So this is x, alright, and plane is that this is along a z axis and a y is this, and the central point is lying on a g prime. Center is lying on a g prime. Okay, now what we would like to do is we would like to find out fringe width. Alright, so I'll give you this. So this is what we find. This is the interference. This is the interference. So again I say this is the line, this is the waveforms. These are the waveforms. Plane waveforms, the plane waveforms. This is the plane waveforms incident on two slits. And you get a wave, spherical wave, and this is interference pattern. You see a bright, dark, bright, dark, brighter. This is what we call as interference patterns. This is what we call as interference patterns. Alright, now what we would like to do is, we would like to find out fringe width, this width. What is the width of this? So width. Oh, I say fringe width. So we will get it like this, like this. All right. So I say this. If this is a center bright, yeah. So this is a center bright O. This is going to be our first bright, second bright, third bright. First bright in that direction, second bright in that direction, third bright in that directions, and this is going to be first dark, second dark, third dark, first dark in that directions, second dark in that directions, and third dark in that direction, opposite directions. So this is what we have. So now what we would like to do is we would like to find out the fringe width. Alright, again if I write it more here, this position, this distance is going to be lambda d by d. This is going to be 2 lambda d by d. This is going to be 3 lambda d by small d. And if I write this is going to be lambda d by small d half. This is going to be 3 by 2 lambda d by small d. This is going to be 5 by 2 lambda d by d. This is what it is. Same you're going to get. You're going to get same. Only difference is you get a minus. This side you're going to get minus. So now, what we would like to do is we would like to find out fringe width. Alright, fringe width. So what is fringe width? The fringe width is what we define as a distance between the two consecutive dark or distance between two consecutive bright. So distance between two, let's say this is how we get a bright fringe is that let's say distance between two consecutive dark, this is the first dark, this is second dark. Distance between the two consecutive dark will give you a width of a bright fringe, and distance between the two consecutive dark are too bright. Distance between the two consecutive bright will give you a fringe width of distance between the two consecutive dark, a bright will give you a fringe width of a dark fringe. A distance between the two consecutive dark will give you a fringe width of a bright. So both are same. So therefore, how you get a fringe width? So fringe width is given by beta, which is equal to xn plus 1 minus xn. Alright. What is xn? If I use xn plus 1 lambda d by small d minus n lambda d, and fringe width would be equal to lambda d by d. So this is the fringe width, and this is going to be lambda d by d, and again this is going to be this. I'm talking about this width. Again, this width is going to be lambda d by d. So fringe widths are equal. Both the bright and dark will have a same fringe width. And then this is the fringe width. And then you could maybe an exam they may ask what is the factor which affects the fringe width. So I have lambda, wavelength of light, d, distance between the slit and the screens, and a small d, distance between two slits. So this is how we get fringe width. Alright, so this is all about interference. This is all about interference. This is where we have. Alright, this is again a diagram which I have. So look at here, whenever you get a peak, these are the peak. These are the peak. Wherever you get a peak, the path difference, these are the path difference. These are the path difference. Wherever you get a peak, the path difference are lambda, 2 lambda, 3 lambda. Whenever you get a valley, this is the valley, right? Wherever you get a valley, the path difference could be a half lambda, 3 by 2 lambda, 5 by 2 lambda. That means this is destructive, other one is constructive. Now look at here. Now whether we talk about bright or we talk about dark, one condition that must satisfy is that one condition that must satisfy all along a particular fringe. Again I am repeating, one condition that must satisfy all along a particular fringe. One condition that must satisfy all along a particular fringe is that constant. This is very, very important. Alright. And this determines shape of fringe. This determines shape of fringe. Alright. So this is again determine the shape of fringe. So let's say before I do a shape of fringe, let's discuss angular positions. So now we have done with the linear positions. And what about angular positions, right? So angular position is this. Let's I'll do this. Let's say this is a theta. Let's say for n bright, position is given by n lambda d by small t. N lambda d by small t. And this is what we have. And let's say this is what we call as xn. We call this as xn. Angle is theta n. And I say this corresponds to angle theta n. And now we would say that what is xn? Xn could be given by theta n divided by theta n multiplied by g. Or theta n multiplied by g. That's what we have. So we say that when this is what we have done in lower class. This is theta and this is some small d. This is capital D and d is going to be. This is what we have done in class 11. The where theta is a radian, right? So now look at here. If this is so, then I say n lambda d by small d is going to be theta n d. So dt cancel out. Angular position is going to be this. This is angular positions. All right. So angular positions. N bright is going to be an angular position of n dark. So it is going to be, this is what we have. So this is what we have. So we define both angular position and linear positions, and this corresponds to linear positions, that is equal to n lambda d by small d. This corresponds to linear position n plus half lambda g by small d. That's you should keep in mind. All right, this is very important. And then consequently we say that these are the peak. This is the condition for peak or constructed interference in terms of phase. So 2 pi phase, 4 pi phase, 2 pi phase, 4 pi phase. For destructive it is pi phase, 3 pi, 5 pi, pi phase, 3 pi, 5 pi. So this is in terms of angle or phase. Previous one we did in terms of path difference. So that's what we have. This as far as angular position is concerned. So angular position is not exactly done in textbook. However, this is very important for examinations. So therefore I did it. Now next point is that what is the shape of interference fringe? The point is, what is the shape of interference fringe? What is the shape of interference fringe? And I say that whenever we talk about interference, the particular fringe, either it is a dark or it is a bright, has to satisfy these conditions. Alright? The path difference between the two fringes, alright, all along a fringe would be always constant. Alright. So therefore, the question is, what is the shape of interference patterns? Alright. So the answer which I have written is hyperbola. Why it is a hyperbola? Answer is that this is S2p minus S1p is a constant. This is hyperbolic equations. This is what we call as hyperbolic equations. Why? Because it is a set of points. This line, this is rotating. This line is a set of points having a constant path different from 2 S1 and S2. Again, I am repeating. All right. So these lines are the set of points having a constant path difference, from S1 and S2. Again, I am repeating. Alright, this is very important. Maybe in exam they may ask that what is the path of what is the shape of interference fringe? The answer is hyperbola. But if you want to know why it is hyperbola, why this happened to be hyperbola, is that look at here, the hyperbolic curves are the curves obtained from the set of points having an equal distance from 2 to foci. Or likewise here, this particular fringe are the set of points having a constant distance, right? Having a constant path difference from S1 and S2. Having a constant path difference from S1 and S2. So therefore, this is what we use. So therefore, I have written here a particular fringe would correspond to the locus of point. Locus means a set of points with a constant path difference of S2p and S1p. This gives you what we call as hyperbolic equation. So the answer is very simple. What is the shape of interference fringe or interference patterns? The answer is hyperbola. Why it is hyperbola? This is the reason. Alright. So therefore, this is going to be a constructive. You see a path difference. This is path difference is lambda, path difference is 2 lambda, this goes on higher and higher, then path difference is going to be greater and greater. This goes on higher and higher. Alright. Alright, so this is the picture. This is the picture taken, right? The laboratory pictures of what we call as interference pattern. Right? So this is now, but then under certain conditions, if a beta is very small, then this looks like this. Right? So under certain conditions, right? So this doesn't mean that hyperbolic curve means it's not too curved. However, it looks straight under certain conditions. All right. And now the next point I would like to discuss is we have done with the shape of interference fringe. Shape of interference fringe. Now, you just refer to textbook. Even in textbook, these two diagrams are written. These two diagrams are there. You go and see it carefully, right? Now, next point is, let's say I have this is S. This is a screen. Let's say this is a center C or O, let's say. And this S is the perpendicular bisector of a screen. This is what we call as perpendicular bisector of a screens. M, S1, S2. And this is what we call as center bright. Center bright. This is what we call as center bright. Now what I'm going to do is, if I move this is to S primes. Now the question is, where would be a center bright? Where would be a center bright? So therefore what we are going to do is, I'm going to take this. Let's say this is going to be angle this is going to be angle phi. Let's say this is going to be angle phi. Alright. And then the central bright would shift down with angle minus phi. Alright. So if you push S above or up, then central bright would go down. The reason is that here also path difference is going to be 0. Whenever we have a central bright, path difference, this is the conditions. Whenever we have a central bright, path difference is going to be 0, right? How come path difference is 0? This is like this. So you would say that path difference is not 0. Alright. So this is the point, right? I have to consider from here. Alright? So I have to consider from here. Considering from S primes, path difference between S1 and S2 at O prime is going to be 0, right? Likewise, if I move, if I put this at S double prime at a down, then the central bright would go up again with the same angle. All right. So this is all about interference, fringe or interference patterns, and this is very important phenomenon and phenomenon of wave. All right. So with this, I come to an end of interference. Thank you.